All right, welcome everyone. Hopefully everyone's not in a food coma. I intentionally did not eat lunch, so hopefully I'll stay awake. So before we get started, just a few introductions. My name's Colin McNaughton. I work for Neve Research. I'm the head of engineering there, and we're based here in Silicon Valley. We're the creators of the X platform, which is a memory-oriented platform that combines aspects of compute, messaging, and data into one platform. So our goal is to make it very easy to write applications that don't compromise on speed, scale, performance, or reliability. We aim to sort of take care of those non-functional aspects of application development, allowing Java developers to write applications with ease and leverage all the benefits of in-memory computing. So all of us here at Neve, we're very passionate about high-performance computing, and today we are talking about machine learning and really how it relates to big data. So I should probably start here by saying I am not a data scientist, so that's important for two reasons. One, if there are data scientists in the room and you ask me hard questions about data science specific stuff at the end of the talk, I won't be able to answer. But two, the way I'm sort of talking about machine learning today is really from the viewpoint more of transaction processing. So although I don't have much experience with data science per se, I am very experienced with what it takes to do transaction processing on systems that at the same time need to ingest and update a lot of data while doing analytics on them. So that's kind of what I do. So where that intersects with machine learning is that machine learning, a lot of what it's about is being able to aggregate together a lot of data from disparate sources and use that data as a bunch of variables that I'm going to feed into a model out of which I'm looking to get some sort of answer that has predictive value for my business. So today I want to sort of introduce everyone to why machine learning puts so much more pressure in terms of the amount of data that we need to analyze in transactional systems, and what some of the challenges are in terms of bringing those machine learning models to production in a way that doesn't actually impact our businesses. So typically we're using machine learning in the front of our in sort of front-facing applications that are sitting and interfacing directly with users. So the SLAs that we're looking at are fairly tight in terms of response time. So we need to, in terms of bringing these data-hungry machine learning models online, we need to do so in a way that's not going to impact performance as viewed by our users. So we'll talk a bit about some architectural approaches you can take to actually implement machine learning in the operational tier, and we'll take a look at what sort of performance and characteristics you can expect from leveraging techniques like these in a use case like fraud detection. So big data and machine learning, they go hand in hand. Before a machine learning model even hits production, our data scientists are faced with a big data problem right from the get-go, and that involves trying to harness all the data that we as organizations have been capturing over the past decade, half-decade. We've amassed these big data lakes of data, and machine learning is a really good way to leverage some value from this data. So we've got a ton of data that we can use. And by training models, say I want to predict credit card fraud, and I have a ton of data sitting in a data lake, I can train a model that will let me know based on a whole bunch of data whether or not that transaction is likely to be fraudulent, for example. So we need a ton of data before we get into production just to train up a model give it a taste of all the data we're going to be seeing in production, and then we need enough data afterwards to validate that the model we've just trained actually has accurate predictive value for what we're trying to do. So that was a long-winded explanation of the training portion of the big data problem, and I'm not really going to talk about that today. But there are some aspects that do feed into bringing machine learning into production. So what does it take to really implement responsive machine learning systems in a transactional front-end system? The basic premise that I'm talking about today is the more data that you can leverage and feed to your machine learning models, the better the predictive output of these models is going to be. And that makes sense, right? The more data I can look at, the more likely I can infer some sort of outcome from that data. So this really is just another flavor of the HTAP or HOPE problem, where I've got highly transactional workloads that are trying to update data as requests are coming into my front-end systems at a really high rate, while at the same time trying to do really broad analytical workloads on that data. And the two of those are difficult workflows to combine together. My big read workloads tend to impede my ability to absorb transactions in my front end. So we'll look at some techniques that we can use to let those two conflicting goals live together in production. Finally, machine learning puts even more pressure on our front-end systems in terms of agility. So a common problem with machine learning, I train up a model, but it degrades over time. As my traffic patterns change, or behaviors that I haven't seen before start hitting my front-end systems, the machine learning model often becomes less relevant than it once was. So there's a bit more pressure on us as operational folks to be able to get new models deployed quickly without much risk to the business. Beyond just the ability to deploy new versions of a model easily, data scientists are always looking for new data to improve their models. So there's an aspect of agility where we want to be able to deploy new systems easily without a lot of fear to collect more data to improve our models over time. So there's an ever-increasing push for agility, and machine learning doesn't really lessen our demand for it. So I've been talking a lot about transactional systems. Just to give you a quick flavor of the types of systems we're talking about. Any system that's transactional and front-facing to a user in general is the type of application I'm talking about. And these are some of the typical ones we run across. So in financial trading, it's often around risk. I want to be able to look at the state of the marketplace, instruments, what are my positions, and anticipate any sort of adverse effect on my bank before it happens. IoT, sensor networks, you've probably heard some other talks today talking about that, where I've got a ton of sensor data and I want to use that data that I'm collecting real time, but also from a historical point of view, to anticipate problems before they occur. Credit card processors, we'll be doing an example of that towards the end, but I want to be able to look at my transaction history as well as the current transaction histories of other similar credit card users in determining whether an authorization should be approved. And it goes on. E-commerce is another big one in terms of recommendation engines and trying to match what I think my user is going to be interested in with potential offers I have, for example. So all of those applications, what they share in common is that they're user-facing and tend to have high request volumes coming in and a lot of data in the application domain. So with the assumption that, like me, everyone else here is not a machine learning expert, I thought I'd just ground us a bit and look at the workflow in aggregate. We talked a bit about the data acquisition phase before, but we've been collecting data for a long time now. The data acquisition phase involves taking that data, normalizing it, cleaning it up, and making it generally presentable for me to do analysis on it to extract the features of that data that are going to be meaningful in a machine learning context. So when we say feature selection, we're really just talking about what variables from this, huge lake of data that we have are actually going to be meaningful predictors of the outcome we're looking for. So you can imagine in a fraud detection use case, maybe a customer's first name is not going to give you much insight into whether a transaction is fraudulent, but perhaps the amount of the transaction would. So that's just what data is meaningful, and not just what concrete variables are meaningful, but what variables in aggregate are meaningful. So the example of the amount of a transaction, that's one data point, but maybe more interesting is how much does that amount deviate from my past transaction history, for example. That's where a machine learning model is going to be really good at sort of picking up that deviance when confronted with a bunch of data. So training, it's a big data problem in that we need to ingest all of this data and move it into whatever framework we're using for training. So it's a huge amount of data that we got to move and process through our model to train it up and test it. So I won't talk too much about that, but that has some similar aspects of just bringing a solution to production in that after we've done our model training, we often want to take these models and deploy them alongside in production to do things like A/B testing. So we need to be very agile in our testing approaches to give a preview of our model's performance before we take it live. But mostly what we're talking about today, what does it take to get these things into production at scale and making them reliable enough for them to provide value to our businesses. Final phase that I'll just touch on briefly is, we talked about it a little bit before, but models degrade over time, so we need really tight controls on monitoring how valuable the models we've deployed are to us over time. So over time, if the accuracy or efficacy of that model is reducing, we need to take action proactively. So today, mostly we're going to look at what sort of features we're talking about collecting and what it takes to bring them to production. So feature selection. It's about determining what variables are meaningful either as discrete values or in an aggregate form. Which of these variables is going to help us predict whatever value we're looking to predict? And how deep do I need to go in terms of data mining to get to the level of accuracy that I want? So the more data that I can feed into these models, or at least the more relevant data, the better my predictive value is going to be. And finally, when thinking about feature selection, what data is missing? Feature selection, I guess there's a little bit of an art to it, but a lot of it is sensible values. If you're trying to predict sale prices for homes, for example, you can imagine square footage, and you can kind of intuit what some of the likely meaningful predictors are going to be. And if you don't have that data, we need ways to collect it so that you can operate on it. So the supposition being more data, you're going to have better models. And that's great if in the lab you can take a look at your data lake's worth of data and come up with a model that's 99.99% accurate. But it's not going to do you a lot of good if you can't assemble all the data you need to feed your model in production, right? So these are front-facing applications, and if it takes me 10 seconds to come up with a list of product recommendations for the user that's landing up on my site, I've likely already lost their interest. So there's a bit of a balance between what I can do offline and in batch fashion and what I can actually assemble in a fast enough time frame while I'm in production. And it's not just the read performance of that data that we need to worry about, because we are also absorbing data that's going to be used for future transactions, future learning, and just for our business objectives. So it's being able to assemble all that data, but at the same time be able to ingest the data that I need to just run my business and gain more intelligence for future transactions. So a couple examples. I gave one earlier of a feature for fraud detection. So the amount of a transaction on its own might be indicative of fraud, but maybe it's how much different it is from transactions that I've done in the past. Or potentially, how much does it differ between transactions, or the amount of transactions at a particular merchant in the past? If I've transacted with Best Buy in the past, but it's all been $10 purchases, maybe there's something a little suspicious about a $5,000 one. Location is increasingly becoming a good data source to look at, but if I know that I made a purchase in San Francisco at 1 o'clock at a point of sale system, and then 2 seconds later there's a point of sale transaction in New York, that should be something we can flag. So this is a sort of geographic disparity in terms of the data that I need to collect and aggregate. And just one more set of examples. E-commerce and personalization. How much do I know about my user? And in particular, some of the same types of variables, time-based stuff, seasonal interests. If I know that Jane goes snowshoeing every winter, maybe I'm going to start tailoring my recommendations to the types of purchases she's made in the past. If I know information about where my user is and what they've enjoyed doing in the past, I might give them offers to go and see a show when they're in New York if they went to a show last time they were in New York. So all of these things put a lot of pressure on our transactional systems because we want to be able to see all this data to make these better predictions. So we've been talking about some of the pressures machine learning puts on transactional systems in terms of just how data hungry they are, but transactional systems, front-facing, still need to do all the things that transactional systems traditionally have done. Machine learning just kind of exacerbates the problems that we're looking at in terms of how difficult it is to do the analytics on the data that we're looking at. So of course, our systems where we're deploying these need to perform and scale. They need to be able to evolve organically with our businesses. We're hoping we're going to be successful and can absorb more traffic in the future. So it can't be that I'm maxing out systems or they're so costly to deploy that it impedes the growth of my business. Nor can I be nervous about adding new functionality or experimenting with new functionality. I need to feel like it's not a very risky thing to deploy new functionality, try out new models because it's either cost prohibitive or I'm afraid that it's going to blow through my performance SLAs. So a really performant, scalable architecture is what we need to empower us to actually take these risks as business users or as users trying to solve a business problem. Closely linked to that is agility. If it's very costly to bring these systems online, I'm not going to be very inclined to try out new functionality or collect new data. And of course, as they're front-facing, they've got to be highly available. So in the context of all of this, we can't afford any downtime, so we need to take that into account in these systems as well. If my transaction processing system's down at Visa, for example, I start losing customer loyalty. My customers are angry, so I lose sort of mind share. And then finally, we can't think about these systems as doing machine learning only. That is not the entirety of the application we're developing. There's still the regular business logic that drives our businesses. So we need solutions that can, at the same time as we're assembling all of this data to feed our machine learning models, which are improving the value of our businesses, we still need to do the actual work that we're doing at the end of the day. So what we want to avoid are situations where we're in architectures where we're doing big scans of data to collect data for machine learning, and then maybe later doing a big scan of data just to feed my traditional rules processing. So we want some sort of mix generally of machine learning, but backed by enough sanity checks so that if the machine learning model goes a little bit haywire or degrades, that we're not going to do anything catastrophic. So planning for scale. This architecture is sort of an architecture of what not to do, but it's a familiar architecture. Now, when I trained my models, I may have all of this data, all this valuable data sitting in a data lake somewhere in a data grid. And the temptation would be to launch several instances of my application, elastic scale them, and I've got high availability by virtue of any of these systems go down. That's not the laser pointer. If any of these go down, any other system can pick up the slack. The problem with this architecture is that because these are update-intensive workflows, I'm trying to update the data that I'm looking to do analytics on at the same time as trying to make those updates. And if I'm trying to assemble a lot of data in a consistent piece of state, that means I'm going to be locking that data. And if I'm locking that data, I can't actually add new data that's coming in by means of my customers' requests. So ultimately, a solution like this just doesn't scale because of the contention between write and read. So what do? No matter what data solution you're using, I think really the only way to get systems to scale horizontally is to start thinking about how to partition my data. So if you imagine an application that's dealing with customer data, I would break that application up and the data for that application across some sort of meaningful business metric, say like a customer ID. And as long as I can route requests to my application to an instance that holds or owns the data for that customer ID, I've made it possible to scale my application wider. I can spread my generally map of customers thinner and achieve greater horizontal scale that way. There are some complications when trying to do aggregate operations across a bunch of customers, in which case you'll have to do some sort of orchestration or join of that data. And we'll talk about that in a bit. But this model does allow you to scale horizontally. As my transaction volume grows, I can spread wider and continue to meet performance SLAs in the front end just by virtue of going wider. This architecture is not perfectly ideal, though. As pictured here, we're showing data separated from the processing applications, and data do not live together. And that's a bit of a problem in terms of these update-intensive and analytically intensive loads, because if I am coming in and trying to iterate, say, one customer's transactions or past transactions, I now have to go and fetch those from a remote data store. That's costly in terms of latency, and in terms of update time. If it takes me a millisecond to, say, update and add a new transaction, and 9 milliseconds to read a customer's transaction data, I'm looking at 10 milliseconds of just data access time, which translates to 100 transactions per second. That's not really great from a high volume transaction processing point of view, and it means I have to scale wider, which isn't good for the bottom line in terms of cost and complexity of the solution. So to get around that data latency bottleneck, one thing you can do is start co-locating data and function together. So by either bringing the data to the function or the function to the data, you now no longer have the latency or data access time associated with either updating that data or iterating through that data. And that's really important, because if I want to look at 2 years of a customer's transaction history, now when the request comes in, I'm just iterating through a list of customer transactions on which I can, at the same time, do my business logic on it and assemble variable data that I'm going to feed to machine learning. So that's really important in terms of being able to dramatically increase the amount of transaction volume that my systems can handle, which in turn is very important because it means I don't have to scale as wide, and it makes deploying these systems a lot more cost effective. One problem with bringing data and co-locating it with function, if I'm keeping that data private to a particular application partition, what happens to my HA story? So now if any of these instances go down, I've kind of lost my data changes, especially if they're sitting in memory. So to fully round out a system like this, you also need some degree of replication to protect against machine or process failure. So by replicating any changes that are made to data to a backup instance that may be sitting in a passive mode, I've now given myself high availability at scale and good performance. So you need these three fundamental pieces no matter what sort of data solution you're looking at. It's got to be in memory. We've got to partition it so that we can scale it. And we need to co-locate the data in function. And we need a replication strategy for high availability. So what I've just described is very closely aligned to a microservices architecture. One of the main tenets of microservice architectures is that data is private to the service that owns it, which fits really well with the architecture we've just talked about. So the only way you can access data in a microservice is by sending it a message and requesting that data in a response. So for the reasons of scalability, cost, and performance, microservices are a really great approach to look into for doing that. And beyond just the scalability and cost savings advantages, from the point of view of machine learning, we talked about some of the agility benefits or demands that we're going to have when deploying machine learning models. So microservices, because they're small units of function around a piece of private state, it takes a lot of the fear that we have about launching a new microservice. I can launch it. It doesn't have to impact anybody else. And if it doesn't work out, that's fine. I just throw it away. And as long as no one else was relying on it, it's totally fine to get rid of. So because they're smaller units, they're easier to maintain. You can have smaller teams working on them, build up centers of expertise around them. And you can generally iterate faster simply because you're not dealing with a monolithic application. Each service can evolve independently according to the demands on it. So looking at microservices for aggregating feature data, this picture is showing a pipeline where I am now collecting pieces of data that I'm going to use to feed to the machine learning models shown in the bottom of the diagram, just in an orchestrated pipeline fashion. So I go to service 1, pick up some data, normalize it, pass that data along to service 2, which then includes it in the final result that it sends to the machine learning model. So I've now picking up all the pieces of data I need to arrive at my result from disparate microservices sitting in my organization. One might ask, if this data is living in hundreds of microservices, can I just daisy chain all of these together sequentially? The answer to that is maybe, as long as your communication pattern between microservices is asynchronous. These processing pipelines don't actually need to take a long time to complete. Modern messaging brokers, you look at your Solaces, your Kafkas, you can do within a data center 10, 100 microsecond hops. So depending on what your actual SLA is, maybe just put these, orchestrate a flow where I'm picking up all the data I need that terminates at a machine learning model or two that generates a result. But if you are nervous about, or you have very tight SLAs, it's also equally possible in a microservices architecture to just orchestrate the collection of this data. So each microservice is holding the data that's valuable to our machine learning model. And I can, as a request comes in, just in parallel, call out to all of the microservices that are needed to collect that data and solicit the data I need in an asynchronous fashion and move on to processing the next request. So that might sound a little bit like I'm going to be saturating my network with a ton of data. But what's sort of subtle about this approach is that it's not like a shared data solution where I'm pulling down a bunch of data, all of it in its raw form, to do analytics on it. But rather, I go to each service, I do the processing that's relevant to my workflow there, and I'm computing the variables that I need for machine learning, and that's the result that I'm returning. So I'm not returning all of the raw data, but I'm returning a much smaller amount of data that's computed by the service that owns that data. and I can do this in parallel, which means that my overall application latency is quite low. So the last thing I want to talk about, if I've sold you on microservices, which I think is really the way to go for building up these flexible pipelines, one thing to think about is the encoding. So we shouldn't have too much data flowing over our network or in our messages, but they are going to be evolving independently. So think a bit about encoding. Maybe JSON's not the best encoding format to send over the wire. It's expensive to encode and kind of large on the wire. So there are plenty of protocols out there, and if you as an organization can standardize on a particular protocol or encoding that works for you, all that you really need is an encoding that evolves gracefully over time. So something like a protocol buffers. If one service adds a field, not every service in your ecosystem needs to upgrade. So think a bit about encoding and think about interaction patterns organizationally as a whole. So you'll probably want some sort of level of governance about how the system evolves as a whole. And I kind of talked about this before, but leave room for your regular business logic. It's not all machine learning, and remember that machine learning is fallible, just like anything else. So what's nice about a microservices architecture is it's very easy to incorporate whatever other business logic you need in line with any sort of data collection. And the last bit of advice I'd give is while developing these data collection flows in your microservices, think about monitoring and measurement from day one. You'll want to be able to manage and monitor how well these systems are doing for you over time. And think a little bit about what kind of data you need to get out to drive future training of models in parallel with what's in production. So think about pushing it out on a Kafka queue asynchronously from the transaction flow if you can. But you're looking for ways to get new data out without it impacting what's happening in the front end. So a bit about what we do in the X platform. It shouldn't surprise you too much. It's similar in spirit to the flows that I've talked about, but what we do is give you a architecture whereby you can model messages and state or data. And we give you two primitives that really make it easy to write these microservices architectures that utilize in-memory techniques. One is the ability to treat plain old Java objects as if they were durable. And the way in which we do that is because we've generated your application state, we know what any one of your message handlers has changed or touched. So if you think back several slides ago, I talked about how you need to be able to replicate any state changes or data changes you make. We'll take care of that under the covers so that in the event of a failure, you can pick up processing where you left off. The other really important piece that we provide is being able to treat messages as just plain old Java objects as well. And when you send a message, we give you the guarantee that it will get to its destination in a once and only once fashion. So as you are working with increasingly distributed systems that may be going down due to machine failure or whatever, you don't want to have to worry about reconciling lost or duplicate messages. It just complicates your business logic. So our HA story, I just mentioned it in the last slide, but generally we give you a model by which we can see what's in your messages, help you route that to a particular application partition, give you the ability to update any state, regular Java objects, and what's most important, the ability to asynchronously replicate any state changes you make to a backup instance ready to take over in case there's a failure. And that's really where our secret sauce lies, is being able to do that without blocking. Because if your replication strategy is a synchronous call out, you're not doing any much better than a remote data storage solution. So when it comes to deploying these for machine learning workflows, on our platform, it looks like any other microservices approach. Every microservice that you launch, you can partition its state. Each one of them is highly available by virtue of replication. So you'll have a primary and one or more backup instances. And through the messaging primitives we give to you, you can communicate with these at high volume, low latency with no loss. So very easy to just start putting together orchestrated flows between microservices that operate on a ton of data that's just sitting in memory as regular Java objects. And that's what we're sort of about. I don't think we need to look at that unless there's a question. So what does a system like this look like? Let me walk you through one of our reference applications. It's a fraud detection app for credit card processing. And so it's a nice simple flow to just understand how you can incorporate machine learning. Very, very simple use case. We have an authorization request that comes in. That authorization request really only has a card number and a merchant ID. What we need is to route that request to a particular customer microservice that's holding that transaction history. So we need to enrich that request with some reference data about who the customer is and some of the merchant data, and then finally leverage all of that transaction history that's just sitting co-located in memory to look at a couple years of transaction history and make a go, no-go call on fraud detection. So on the X platform, it looks something like this. We'll be just sending requests in. It goes first into a microservice that does a simple mapping from a credit card number to a card holder. So it's got customer profile information. That service runs with a primary and backup and is partitioned just by card number. So very easy to scale that out. It's got very few computing demands on it. And same one with the merchant applications. So we pick up some customer details. Next stop, we go to the merchant service, which just holds merchant information by merchant ID. We further enrich that request, and then send it to the correct instance that's holding the card holder's transaction history. And that's where we do a large iteration over all that customer's transaction history, computing vectors that we're going to pass on to a TensorFlow step immediately following that. So we're doing regular business logic checks there and assembling data and variables that we're going to feed to machine learning. So by employing a microservices architecture like this, by keeping everything asynchronous, no callouts for data, just a simple flow like this easily sustains 7,500 transactions per second with an end-to-end latency of something like 1.2 milliseconds. And that's important because if we look back at this flow, that's eight messaging hops that we're doing, and it's not so bad when you think about what that overall response time is. So this is just running on 3 machines in our lab, and that does basically a quarter of Visa's peak transaction processing load. So you can imagine just scale this a little wider, and it's a pretty cost-effective solution to reveal all of that customer's transaction history as it's happening and as it's being updated. And that slide just says the same thing as the last one. So that's it for me today. Feel free to check that application and solution out. It's on our website. And if you like, just drop us a line. I think I've got a few minutes for questions if there are any. Yes?
So maybe I missed it. What was the data retention that you had in this? Like how many transactions for a particular customer?
So we modeled it off of 2 years of transaction history. And we gave each customer 2 credit cards. And we put 700, I think it was 700 transactions median per card holder. So it's like 1,400 transactions total. And back here on this slide, you can see this dashboard. This is our management and monitoring console. But that is showing the amount of time it's taking us to iterate through those 1,400 transactions, so 110 microseconds. that last step using TensorFlow, about 97 microseconds to run through the TensorFlow model. So it's kind of nice because you can separate out the machine learning aspect. We don't have GPUs in our lab, but if you did, microservices allow you to deploy on the machine learning step on maybe more specialized hardware and scale it more towards demand. Whereas in the cardholder services, once you're thinking about holding a ton of customers, you're probably going to want machines with bigger memory footprints. Also, a fair amount of CPU because you've got a lot of work to do while you're scanning through them. Any other questions? Yes?
So about collocating the data and processing. So historically, like people said, like always put application server where your database is. Then Hadoop said like collocate the processing and data. But recently, people use more and more like cloud storage and process data elsewhere. In your platform, you can say like we collocate, but we also use external machine learning. So like, is there like a good answer, or like it depends on the use case?
So for these flows that you need the absolute fastest access to a lot of data, you want to be doing that iteration right next to the data and the processing on it. It doesn't preclude you from siphoning that data out into a data lake that sits elsewhere, but the important thing is that the owner of that data is a single service, because as soon as you start letting two processes access that data, then you start getting into data contention problems. So if you want the absolute fastest access to data and you're looking to do that in microseconds, it's really best to partition that data out and bring the function to the data, or vice versa. Did that answer it? Or maybe I didn't quite get your full question.
It depends, like, to be honest. Like, also, some people say like use Redis cluster like for these protocols, right? To share the data between.
And knock yourself out if that works for the solution, but just it depends on what the data access time is and how much data you have to pull down from Redis to process on it. If you can process in Redis and it solves all of your processing needs, then that's a totally valid architecture as well. The important thing is how many different threads of control are trying to update that data or look at it at the same time.
And your answer, like, use it on the same thread, on the same memory space?
Single-threaded writer, or a single writer principle is definitely our answer to it. And so down to the core, we'll try to co-locate the same data on the same processing core just to use the processor cache most efficiently. Yes?
So are you using any kind of hardware accelerator for the inferencing?
The question was, are we using any kind of hardware accelerator for the inferencing? Not in this demo. So we don't have a GPU just on the machines. We ran it on the lab. But it's regular TensorFlow. So if you did have GPUs, presumably that number would come down.
Yeah. We're doing about like 97 microseconds.
Yeah, it seems a little high to me. So, but that's kind of the beauty of it. Just deploy it on a machine that does have it. Cool. Anything else? Well, if anything occurs to anyone, come find me. I'll be hanging out at the Neve booth later. So thanks for coming today.